Well, welcome back. We are marching on in our Calculus 2. We are looking today, continuing to look at integration and techniques of integration. So one of the things that we traditionally look at when we do that is how to approximate a definite integral. That's what we're after today, how to approximate a definite integral. And some of this is familiar to you from Calculus 1. You had some function from A to B. You were looking to approximate the definite integral from A to B of f of x dx. And so you let this be x sub 0, and you picked a couple of random x values in between, or maybe they were evenly distributed or what have you, so this becomes like x4. And you did things like a left rectangle approximation method where you use the left endpoint to determine how high a rectangle is, the left endpoint to determine how high a rectangle is, the left endpoint determines how high the rectangle is, the left endpoint determines how high the rectangle is. And then sometimes we used an RAM, we used a right rectangle approximation method. The right endpoint tells you how high the rectangle is, the right endpoint, the right endpoint, the right endpoint tells us how high the rectangle is, and so we add up the areas of 4 rectangles, and that gives us the approximation. Sometimes, very rarely, we used an MRAM where we would let the midpoint determine how high the rectangle is. We'd let the midpoint determine how high the rectangle is. We'd let the midpoint determine how high the rectangle is. We'd let the midpoint determine how high the rectangle is. Nobody liked any of those. There are two other ways to approximate an integral that I would like to describe for you in our time together. So we're going to pretend we have some function. It's continuous from A to B, and A is the x sub 0, B is the x sub n. So there are going to be n little subintervals. There are n little subintervals, x1, x2, x3, x4, and they just keep going. That's x sub n minus 1 all the way up to x sub n. What if instead of letting the right endpoint or the left endpoint dictate what our rectangle is, what if we didn't use rectangles at all? What if we used trapezoids? This shape is a trapezoid. This line segment is parallel to that line segment. This is not parallel to that, and so that's a trapezoid. So what I'd like to do is I'd like to talk about the area approximation using trapezoids. Well, the area of a trapezoid is height over 2 times the sum of the bases. So that's fine because that's the height, and that's a base, and that's a base. That's the height because it's perpendicular to both of those sides. So when we do that for this trapezoid and this trapezoid and this trapezoid and this trapezoid all the way apart, all the way across, well, what ends up happening? So the integral from a to b of f of x dx is approximately, well, we're going to pretend that each of these has the same height because that's going to be convenient. So there's going to be an h over 2 all the way across. What is that h? Well, that h is this distance. This distance is the distance between the x's, so that is delta x over 2. And then what do we have? We have this base plus this base, and then this base plus this base, and then this base plus this base, and then this base plus this base, and all the way across. So the first base gets counted once with the first trapezoid, the last base gets counted once with the last trapezoid, but every other base counts twice. So we have the first base, and that's a function value, and then 2 of the next one, and then 2 of the next one, and then so on, until the last one. So one of these, two 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 of these, one of these. That's the way it goes. That's the trapezoidal approximation. And it happens to be, for reasons that I can draw in a moment, it happens to be the average of the left endpoint approximation and the right endpoint approximation. The trapezoidal approximation happens to be the average of the left endpoint and the right endpoint. For example, approximate the integral from 0 to 2 of x squared dx with a trapezoidal approximation for subintervals. For subintervals. So here's x squared on 0 to 2. We want 4 little subintervals, so we break this up into 4 little subintervals. And the trapezoidal approximation with 4 subintervals is delta x over 2. What's delta x? And then we've got this y value, 2 of those, 2 of those, 2 of those, this y value. So first y value, then 2 of the next, 2 of the next, 2 of the next, last y value. How do we get those y values? We take these x values and stick them into our function. So this y value is 1/2 squared, and this y value is 1 squared, and this y value is 3/2 squared, and this y value is 2 squared. And so you add them all together, and you get 11/4. It's the trapezoidal approximation. If 1 is good, 2 is better. Integral from 0 to pi of sine x dx with a trapezoidal approximation for subintervals. So 0 to pi looks like this. We want 4 subintervals, so we split this up into 4 little subintervals. We want the trapezoidal approximation with 4 subintervals. That's a delta x over 2. Delta x, that's this distance. That's the distance from 0 to pi over 4. And then we've got the first y value, the last y value, and then 2, 2, 2. The one in the middle is really easy. The sine of pi over 4 is known, and the sine of 3 pi over 4 is the same. And so you crank all that out, and you get pi over 8 times 2 plus 2 radical 2. So you may wonder aloud, is that good? Is that good? How good is the trapezoidal approximation? How good is it? So here's how good it is. Let capital M be an upper bound for f double prime's absolute value on A to B. In other words, you graph f double prime and you find the highest high or the lowest low, whichever is further away from the x-axis. If the highest high is further away, then that's m. If the lowest low is farther away, then its absolute value is m. We're looking for the biggest that f double prime differs from 0 on AB. Then the error on the trapezoidal rule is less than or equal to that capital M times b minus a cubed over 12n squared. You will never, ever, ever be required to know this. Ever, 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 ever. But it is worthy to note, the more subintervals you have, the more n is, the more the number of subintervals is, greater the denominator is, which means the less the error is. The farther apart A and B are, if B minus A gets bigger, then that makes the numerator bigger, and that makes the error bigger. And so those are things that make sense for us to think about. I've got another rule. It's not a trapezoidal rule. I've got Simpsons Rule. We won't prove why Simpsons Rule works so nicely because Simpsons Rule doesn't deal with line segments at all. It deals with parabolic splices. So what does that mean? So you've got some function from A to B, and so this is x sub 0, and this is x sub n, and so you break things up. What Simpsons Rule does is it says we're going to put a parabola through these 3 points, and then we're going to put a parabola through these 3 points, and we're going to do areas that way. So what Simpsons Rule says, I'm going to go orange for this. What Simpsons Rule says is that the area under the curve is approximately delta x over 3 times, then you do the first one, 4 of the next, 2 of the next, and then you alternate 4, 2, and so on. 4, 2, 4, 2, 4, 2, 4. It's 4 of the next to last, and then the last. So one of these, one of those, and then 4, 2, 4, 2, and so on. That's how Simpsons Rule works. It's easy to demonstrate. Let's approximate. Oh, this is example 3, I suppose. We approximate the integral from 0 to pi of sine x dx with Simpsons Rule for intervals, for subintervals. We'll still go with that. So that's delta x over 3, and you know from before that that's delta x over 3. So then it's first, last, and then 4, 2, 4. 4, 2, 4. And this turns out to be pi over 12 times 4 radical 2 plus 2, whatever that is. Simpsons Rule is much, much stronger than the trapezoidal rule is. The error on Simpsons Rule is less than or equal to capital M times b minus a to the 5th over 180 n to the 4th, where capital M is an upper bound on the 4th derivative. So you graph the 4th derivative, you find the highest high or the lowest low, whichever is further away from the axis. This number gets really, really big really, really fast. So Simpsons Rule is a much better approximation than the trapezoidal rule. I have to give us 2 OYOs super quick because our time is almost up. I want to approximate the integral from 1 to 7 of 1 over x dx with the trapezoidal rule 6 subintervals and Simpsons rule 6 subintervals. That's that. We're off and running. Our 15 minutes are up.